was worried about a number. In the 1940s, he had worked out how electrons interact with light, an insight that earned him a Nobel Prize. But a particular number bothered him. All good theoretical physicists put this number up on their wall and worry about it. Immediately, you would like to know where this number comes from. Nobody knows. It's one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. That number was the fine structure constant. It sits at the heart of Feynman's theoretical success, quantum electrodynamics. It is a number that tells us about the strength of electromagnetism and has a value close to 1 divided by 137. Feynman's theory cannot calculate this number, and his equations are impotent until you measure its value in an experiment. And scientists today are still asking the same question that Feynman did 70 years ago. Where does this number come from? And it is not alone. Our physical theories are awash with constants of nature. They dictate how the fundamental pieces of the universe operate, how electrons repel electrons, and how gravity draws matter together. Some of these constants are familiar, such as the speed of light and Planck's constant. Others, such as quark mixing and Yukawa couplings, are found within the complicated mathematics of physics on the edge. And without measuring and calibrating these numbers, all physical theories would be useless. The constants of nature are clearly central to all physics, but they appear to play a pivotal role in an even bigger question. How are we here? To understand this, we are going to have to take a journey into ourselves. Peeling apart a human, we find a complex mix of organs and fluids. As we peer closer, we find that these are built from a diverse range of individual cells, each interacting to perform the task of the liver, or muscle, or the brain. Closer still, each cell is revealed to be a sea of complexity, a wealth of smaller elements, ribosomes and chromosomes, cytoplasm and mitochondria, each playing a part in the running of the cell. The pieces of these cells are composed of molecules, proteins and lipids, DNA and RNA. Each level so far has uncovered a wealth of complexity, but as we go further, simplicity appears. Molecules are built from atoms, with each complex arrangement enabling the complex interactions with others. But chemistry tells us that there are only 92 natural elements, from hydrogen to uranium, so only 92 different kinds of atoms are available. Entering the world of the subatomic, an even simpler picture is uncovered, with each atom being a mix of 3 different particles, protons and neutrons within the atomic nucleus with orbiting electrons. And the protons and neutrons are also composed of smaller particles, known as up and down quarks. Here, at this fundamental level, we find that matter, people, trees, planets, and stars, are nothing but different arrangements of these quarks and electrons. Of course, these pieces need glue to hold them together, and for fundamental particles, this is provided by the fundamental forces. Atomic nuclei are held together by the strong force. Atoms hold onto electrons with the electromagnetic force. Gravity draws matter together to form planets and stars. In the mix also is the weak force, which can influence the stability of atoms. Simply put, we are built from the ground up. Our physical existence in this universe is nothing more than the manifestation of a huge number of interactions of its fundamental pieces. And all these interactions are dictated by the values of the constants of nature. But where did these values come from? Does the cosmos have to be this way? And was the fundamental universe primed from the Big Bang to now to necessarily produce the complexity that appears to be essential for life? These seem like strange questions. We have only this universe with the values of these constants of nature revealed to us by experiment. They appear to be written into the very fabric of existence. But science is built on what-if games, pondering how things would change if the situation were different. what-if questions have the potential to answer not only the question of how we are here, but maybe even why. This video is sponsored by Magellan TV, the documentary streaming service. Question: at the speed of light, how long would it take to travel to Andromeda, our nearest galaxy? A. 500 years, B. 2.5 million years, or C. 25 million years? That's right, it's 2.5 million years and infinite energy. Probably not worth it. And so, our recommendation this week is the documentary Faster Than Light, The Dream of Interstellar Flight, a fascinating exploration of the different possibilities when it comes to venturing towards our nearest neighbours. Antimatter drives, warp speed, laser engines explore the wild edges of theoretical science. Magellan are a sort of Netflix for documentaries, with more than 3,000 documentaries to choose from on a wide range of topics. So, click on the link in the description for an exclusive, month-long free trial for History of the Universe viewers. Thanks. Standing here on Earth, it is easy to think that the universe was made for us. It feels like we are at the centre of everything, with the sun and the stars whirling around us. Indeed, as human civilization began, our cosmic location was written into our developing religions. To the ancient Babylonians, our flat, circular Earth was surrounded by an infinite ocean of chaos. The Greeks and Romans saw the patterns in the stars as a storyboard of myths and legends, of gods and monsters. In China, the universe was arranged in rotating shells, centered on the Earth and containing the stars and planets. But science has since stripped away this illusion. In 1543, the astronomer and mathematician Nicolaus Copernicus displaced the Earth, placing the Sun at the centre of everything. The dethroned Earth orbited this fiery heart of the universe. The coming of the 20th century saw us demoted further. As massive telescopes peered into the heavens, it became clear that the Sun is but one of billions of other stars within our Milky Way galaxy. And now we know the Milky Way is one of potentially trillions of galaxies in the observable universe. Whilst Hubble charted the cosmos, measuring immense distances between the galaxies, Einstein, Friedman and Lemaitre found it to be evolving and expanding, born in an event 14 billion years ago we now call the Big Bang. But where does that leave us? One possible answer came from the ever-insightful Douglas Adams, who wrote in his comic novel Hitchhiker's Guide to the Galaxy, "Far out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow sun. Orbiting this at a distance of roughly 92 million miles is an utterly insignificant little blue-green planet, whose ape-descended life forms are so amazingly primitive that they still think digital watches are a pretty neat idea." But far from just a punchline, our irrelevance in the cosmic scheme of things has become a central tenet of science. Dubbed the Copernican principle, we have developed our scientific theories based on the idea that we are nowhere special. The view from the Earth is essentially the same as from any other vantage point in the immense universe. We are little more than cosmological bystanders. Or are we? In the 1960s, Princeton astronomer Robert Dicke was seeking to understand the origin of the universe. He was a polymath, making important discoveries in atomic physics and Einstein's general relativity. Born from his thoughts on the birth of the universe, Dicke had been thinking about our cosmic location, not in terms of space, but in terms of time. He realized that living thinking beings like us cannot exist at any random time in the life of the universe. In the first couple of billion years, the universe was devoid of carbon, oxygen, and other heavy elements, as these were still deep inside the first cosmic generation of stars. Until these stars died, the raw material for complexity and life was absent. And 100 billion years into the future, all stars like the Sun would have died and become white dwarfs. The dominant stars in the universe would be the puny red dwarfs, faint little stars whose prospects for habitability are small. So, he realized that there was a window of time between the early and late universe where life could thrive. A golden age of habitability. And, of course, we should not be surprised to find ourselves living during this time of cosmic history. We are not observing the universe at a random point in its immense lifetime, Dicke posited, but during a period that allows us to be here. Whilst this may not feel particularly insightful, it does shake the foundations of the Copernican principle a little. The situation became more complicated in 1973. At a conference held in Krakow, Poland, to celebrate the 500th birthday of Copernicus, Australian physicist Brandon Carter gave a speech. And he had Copernicus squarely in his sights. For humans observing the universe, he said, "Although our situation is not necessarily central, it is inevitably privileged to some extent. For us to be here, generations of stars living over billions of years are required to turn hydrogen into the heavier elements essential for our existence." But Carter went further. The lifespan of a star is determined by the physical processes in its heart. Gravity squeezes the stellar core, driving it to immense densities and pressures. In this environment, new elements are forged, with the rate of nuclear cooking determined by the other fundamental forces, electromagnetism and the strong and weak nuclear forces. These elements forged in stars include the iron in the Earth's core and the silicon in its crust. It includes the oxygen in the water of our oceans and the carbon that is the basis for all life on the planet. And so, Carter first coined a new concept in contrast to the Copernican principle. The anthropic principle was born. Our very existence some 14 billion years after the birth of the universe is because of the extremely delicate balance of the fundamental forces that govern the life cycles of stars. And so, taking all of this into account, we are left with a question. If we are so privileged, what would happen if that were to change? What if gravity were a little stronger, or electromagnetism a little weaker? What if the rules of the universe were different? In 1900, Max Planck was desperate. He had been struggling to understand how objects glowed as you heated them, from red to white hot. Like others, he had been trying to use the theory of light written into James Clerk Maxwell's theory of electromagnetism, and, like the others, he had failed. In his desperation, he threw out the classical ideas of heat and energy. Thinking he had introduced little more than a mathematical trick, Planck had unknowingly invented quantum mechanics. But this trick, this quantization, worked, and Planck would win the Nobel Prize in 1918 for his insight. Nestled in his equation was a number central to his result. Today we call this number Planck's constant, in honour of its discoverer. And this number now has a central role in quantum physics, explaining not only how hot objects glow, but atomic structure, the interaction of matter and light, and a myriad of strange quantum effects. It is a constant of nature, and these numbers are essential for studying hypothetical other universes. Physics is written in the language of mathematics, and through mathematical equations we make predictions on how objects behave. When we want to understand the motion of the moon, we can combine Newton's laws of motion and gravity to predict where the moon will be tomorrow, or in a week, or in 1,000 years. When we want to understand the flow of electricity, we can use Maxwell's equations of electromagnetism and the properties of electrons to deduce the expected reading on an ammeter. But the equations of physics are not purely mathematical. You cannot determine how things evolve from mathematical manipulation alone. There is another vital ingredient that has to be added: the values of the constants of nature. In Newton's theory of gravity, there is the gravitational constant, and without knowing its value, the equations are sterile. In electromagnetism, there are the permeabilities and permittivities of electricity and magnetism. Without knowing their values, Maxwell's equations are muted. And to determine the value of these constants, scientists must ask nature. They have to measure them. The year is 1798, and Henry Cavendish is about to run his experiment one more time. He places his eye to the telescope, which is not faced towards the heavens, but through brick, poking through a small hole in the wall of a shed in his garden. So as not to interrupt the incredibly delicate apparatus, he has placed it inside a wooden box within the shed, protecting it from wind and the outside world. The equipment itself measures the strength of gravity between lead balls, using an incredibly sensitive torsion balance. And with it, Cavendish was able to measure the density of the entire Earth, weighing the world, as he called it, a result which led directly to the calculation of the gravitational constant, with accuracy not exceeded for another 100 years. And this quest for exactness continues to this very day, with the constant, g, known to 6 decimal places. And it's not just gravity. Measurements for the speed of light, which is the ultimate constant for electromagnetism, and Planck's constant, have been refined over decades. They are joined by more esoteric values, such as the strength of the Higgs field and the mixing angles of quarks. As well as the constants of nature, there are other values of the universe that cannot be deduced solely from mathematics, and so must be discovered. These include the masses of the fundamental particles, such as the quarks and electrons, that comprise all of matter. These values are in fact so important that physics textbooks tabulate them, so readers can use the equations of physics between the covers. Of course, the constants tend to have units, and so changing from meters and kilograms to feet and pounds will mean that the value of the constants will change. So scientists focus upon combinations of the constants that are dimensionless. A proton, for example, is 1,836 times heavier than an electron, if the masses are measured in kilograms, pounds, or troy ounces. But why 1,836? Why do the constants have the particular values they do? How would the universe have been different if this ratio had been 18 or 18,000? And so we return to the fine structure constant. Why is it 1 divided by 137? Theoretically, these are questions we can start to answer. We can solve our equations of physics when considering different values for the fundamental constants. With this, we can calculate what would happen in the hypothetical universe if gravity was 1,000 times stronger than in our universe, gripping the Earth more tightly in the Sun's grip, making us orbit more rapidly. But this is not quite what we are searching for. If we want to know how the universe would have turned out if the constants of nature had been different, we must consider the evolutionary history of the cosmos, with a different strength of gravity or electromagnetism, or heavier electrons, or some other mix of different physics. We have to go back to the beginning. Naively, we may think that this might change the time period when complexity and life could have arisen in the universe. If gravity was increased, that would increase the rate at which nuclear reactions could happen, meaning heavier elements, and hence life, could have appeared earlier in the universe. But this, as scientists have discovered, is thinking far, far too small. Astronomers have had great success in explaining our universe playing by the rules. Around the globe, teams of scientists are building their own synthetic universes, translating the equations of cosmology and astrophysics into computer code. With the aid of supercomputers, they can trace the complex interplay of matter and radiation in an expanding universe. As computer power has grown, so has the scale of the synthetic universes, with projects such as the illustrious TNG or the Next Generation tracing the cosmic evolution of a cubic chunk of synthetic universe a billion light-years on a side. Over the billions of years within these synthetic universes, cosmic expansion acts to pull matter further apart, while gravity acts to draw it together. Mass clumps into proto-galaxies whilst the computers solve the equations for the flow of gas and the formation of stars. Within these synthetic universes, stars live out their lives, some exploding spectacularly as supernovae, whilst others expire with a final puff. All the while, the computer programs are tracking the formation and dispersal of elements as generations of stars come and go. An inspection of these synthetic universes reveals rich structure, with synthetic galaxies and clusters, clouds of pure gas left over from the Big Bang, and other clouds polluted with heavier elements. These synthetic universes look just like ours, a confirmation that the universe we see around us is imprinted and shaped by the physics underlying the cosmos. And the same is true for our existence. The presence of complex molecules composed of atoms is also a manifestation of this physics of the fundamental, the result of stars being able to undergo nuclear burning at their cores. Of course, if we can generate a synthetic universe on a computer, or even with paper and pencil, for the physics of our universe, it seems that it should be simple to think of different physics in hypothetical universes. All we need to do is to change the numerical values of the constants of nature. Maybe we just tweak our computer code, press go, and see how early or how late life arises, or how many arms or legs we end up with. But is it really that straightforward? We are the result of a complex web of physical interactions over the billions of years of the life of the cosmos. And to truly answer the question of habitability, we must understand how cutting the web, or even forging new pathways, impacts the existence of the complexity needed for life. A limited view might come from simplified cases, but to truly capture the complexity, scientists turn to the power of supercomputers to churn through interweaved equations. They are still unraveling the habitability of other universes. But as they survey the multiverse of possibilities, the view is a grim one. Calculations reveal a vast ocean of darkness and death. Almost every other possible universe appears to be lifeless and sterile. In many universes there is no structure, no galaxies, stars and planets. In others, no complexity, no periodic table of elements. Dotted among the dead universes, there are little islands of complexity and potentially life, but these are almost vanishingly rare. Let's consider some examples of what happens when you play with the constants of nature. In our universe, the relative masses of the fundamental up and down quarks mean that the proton is lighter than the neutron. This means that neutrons decay into protons, and so, just after the Big Bang, the cosmos was awash with protons. These protons are the hearts of every hydrogen atom, providing the universe the potential to form stars and heavier elements. Ultimately, this endowed our universe with the potential to create us. Messing with the masses of the quarks can have a radical effect. If the down quark was lighter, the neutron would be less massive than the proton. In such a universe, the Big Bang would have resulted in a sea of inert neutrons. Stars of neutrons would form, but no nuclear fires would burn. In this universe, there would be no periodic table of elements. There would be no complexity. There would be no life. Instead of quarks, we could consider the mass of the electron. Zipping around the nucleus, these dictate the world of chemistry. of how matter can join into molecules and crystals. In our universe, the nuclear force is thousands of times more massive than the electron. But if the electron were more massive, its high-speed orbit would cause the nucleus to rattle around in response. This rattling would impact the ability of atoms to bond together, and there becomes a point where nothing but individual atoms could exist. Everything would be a gas. With no molecules and no solids, the prospects for life are bleak. And a universe with a different force of gravity is equally dramatic, if not more so. Firstly, it is gravity that is responsible for drawing matter together in the early universe, forming the first stars and galaxies. If gravity was too weak, then the expanding universe would have remained an ever-thinning soup of hydrogen gas. If gravity were too strong, then matter would be quickly drawn into numerous black holes, locking away the atomic material needed for life. And even between these two extremes, gravity plays a pivotal role. The lives of stars are dictated by the influence of gravity, squeezing the stellar core to the point where nuclear reactions can ignite. Squeezing too weakly will result in stars being nothing more than immense balls of cooling gas. Squeezing too hard means that the nuclear reactor would kick into overdrive, burning through the available material in much less than the 10 billion year lifetime of stars, like the Sun. Long-lived, stable stars appear to walk a knife edge when it comes to the strength of gravity. And finally, even changing the values of things that we've only just discovered would have an enormous impact on habitability. In our universe today, dark energy is the dominant component and is driving the expansion faster and faster. In the early universe, matter dominated, steadily slowing expansion until dark energy took over roughly 5 billion years ago. This slowing expansion in the early universe gave gravity the time to draw matter into stars and galaxies. In the distant future, dark energy will dilute the universe to such an extent that each galaxy will appear alone in the darkness. But if there were more dark energy in the universe, it would have dominated earlier. It could have started its accelerated expansion a lot earlier before matter had the chance to collapse into the first stars. In such a universe, individual hydrogen atoms would find themselves alone in cold, empty space. The prospects for life would have been negligible. And there are many more components of the universe we could consider, such as the speed of light, the scalar of quantum mechanics, or the stability of dark matter. For some of these, the range over which complexity and habitability results can be relatively large, but for others, a percentage change here or there can have a dramatic impact. Consideration of each aspect of physics rules out a chunk of hypothetical universes that could ever host life. In this sea of potential universes, ours is the exception, not the rule. In this sea of potential universes, we are effectively alone. And so, we have answered the first question. How are we here? We are the result of an almost perfectly balanced selection of rules interacting over 13.8 billion years. But now, the second question rears its head. Why? The constants of nature have always had a mystical aura to some physicists. There must, they feel, be some reason for their particular values. Some have even turned to numerology. Sir Arthur Eddington, astronomer at the University of Cambridge and the first person to conduct an experiment to verify Einstein's general theory of relativity, fell into this trap. Like Feynman, he was consumed by the fine structure constant, thinking that it might be exactly 1 over 137. He concluded that this value was related to the total number of protons in the observable universe. But as measurements of the fine structure constant became more accurate, it was realized that it was not 1 divided by an integer value, and Eddington's idea was quietly dropped. But the connections between the constants of nature might be telling us something deeper. As our scientific theories advance and disparate pieces are united as one, the number of these constants needed to describe the universe decreases. Before Maxwell, 2 separate constants were needed: one to describe the action of electric phenomena, and another to describe magnetism. Within Maxwell's equations, these two numbers were united into a single constant of nature, the speed of light. And so, is this the answer? If physicists work hard enough to produce a theory of everything, will all of fundamental physics be unified? No constants left, just pure mathematics. The notion of this ultimate theory is currently a moonshot idea in physics, and it might not exist. But a moment's thought also reveals that this would not really provide us with an answer. We would just change the question. Why then would these mathematical expressions allow us to be here? It offers us nothing but another vast graveyard of dead, alternate universes with no explanation. And the question would still remain, why is the physics just right enough for us to be here? To some, this fine-tuning of the physical properties of our universe is because there is a fine-tuner, a divine being that made the universe for us. Of course, this fits neatly with a lot of religious ideas around the globe, and the fine-tuning argument is often taken as evidence for the existence of at least one God. But there is an alternate idea. University of Oxford philosopher Nick Bostrom has noted that we understand the universe by simulating pieces of it on a computer. In the future, when computers become more powerful, we will be able to simulate more of the complexities of the universe to finer detail. Perhaps our computers will grow so powerful that conscious beings will be part of the program. And maybe these beings will happily exist in their universe without realizing their reality is nothing but a simulation. And maybe, in the future, we won't just simulate one universe, but a variety of universes, each with differing laws of physics and properties. Of course, we will not simulate boring universes where nothing happens. No, we will focus our resources on interesting universes with interesting things, like life. And Bostrom takes this idea of simulated universes one step further, and wonders if it has already happened. Not inside our universe, but with our universe being simulated within someone else's. Our laws of physics are nothing but executing computer code. So are thoughts and experiences of reality. So we should not be surprised to find ourselves in such a universe as the great programmer in the sky above is expending their computational resources on us. An interesting simulation. This idea is loved by philosophers, but scientists not so much. What can we do with this concept? How do we test we are in a simulation if all we do is express computer code as the laws of physics? And of course, there is the problem of whether the universe above is a simulation also. And we are left with turtles all the way up. But there is one more idea that science has posited. What if all these possible universes are not hypothetical? What if they are real, distinct universes out there in a real multiverse? We don't yet have a definitive theory of a multiverse. It is more of a collection of disparate ideas. But perhaps within the multiverse there is a process that generates individual universes. Each universe born with its own distinct set of physical laws, selected at random by some roll of the metaphorical dice. Even our own universe, if started again, could have been born with different physical laws. Of course, in the multiverse picture, most of the individual universes are dead and sterile. In this picture, we were lucky. We got that roll of the dice that allows us to be here. The concept of the multiverse is not universally loved among cosmologists, with declarations that it is extremely wasteful to have all these dead universes so ours could live. Others point out that the multiverse is not really a theory, as there is no mathematics to back it up, or predictions we could test, as those other universes will always remain disconnected from us. And so, the question remains. The whims of gods, computer simulations, or multiverses. Perhaps one of these will eventually give us an answer, or something stranger still. But before that time, considering both the how and why of our existence still has a lot to tell us about the universe and our place in it. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. And we'll see you next time.